term by term integration statement. If a series sigma fn converges uniformly to f on closed interval ab and each term fnx is integrable, then f is integrable on closed interval ab, and the series sigma integral a to b fnx d alpha converges uniformly to integral a to b f of d alpha on closed interval ab, that is integral a to b sigma n varies from 1 to infinity fnx d alpha equals to sigma n varies from 1 to infinity integral a to b fnx d alpha. Now proof: let Snx equals to f1x, f2x, f1x plus f2x plus so on plus fnx. Since each of fn is integrable, therefore their sum is also integrable, which implies Snx belongs to R alpha. Since sigma n varies from 1 to infinity, fnx converges uniformly to f on closed interval ab, so Snx converges uniformly, say, to s of x on closed interval ab. Then for the given epsilon greater than 0, there exists m belongs to n such that modulus of Snx minus s of x is less than epsilon upon 2 into b minus a for all values of n is greater than equal to m and x belongs to closed interval ab. Equation 1. From 1 we have minus epsilon upon 2 into b minus a is less than Snx minus sx, which is less than epsilon upon 2 into b minus a, which employs minus epsilon upon 2 into b minus a minus Snx is less than minus Snx is less than epsilon upon 2 into b minus a minus Snx, which employs epsilon upon 2 into b minus a plus Snx is greater than minus epsilon upon 2 into b minus a plus Snx, which employs minus epsilon 2 upon 2 into b minus a plus Snx is less than s of x is less than Snx plus epsilon upon 2 into b minus a. Equation 2. Now from 2 we have s of x is less than Snx is plus epsilon upon 2 into b minus a, which employs upper Roman integral s is less than upper Roman integral Sn plus epsilon upon 2. Since Sn belongs to R alpha, this is equation 3. Since Sn belongs to R alpha, so upper Roman integral Sn equals to integral Sn a to b integral Sn. Then 3 implies that upper Roman integral s is less than Roman integral a to b Sn plus epsilon upon 2. Similarly, from 2 we have Snx minus epsilon upon 2 into b minus a is less than s of x. This is equation 4. So s of x is greater than Sn minus epsilon upon 2 into b minus a, which employs integral lower Roman integral s is greater than lower Roman integral Sn minus epsilon upon 2. Equation 5. Again, since Sn belongs to R alpha, so which employs lower Raman integral Sn is equal to integral a to b Sn, then 5 implies lower Raman integral S is greater than integral a to b Sn minus epsilon upon 2, equation 6. Subtracting 4 and 6, we get 0 is less than upper Raman integral S minus lower Raman integral S is less than equal to integral a to b Sn plus epsilon upon 2 minus integral a to b Sn plus epsilon upon 2 equals to epsilon, so which implies upper Raman integral S minus lower Raman integral a to b S is less than epsilon. Since epsilon is arbitrarily small, so integral lower upper Raman integral minus lower Raman integral S, upper Raman integral S minus lower Raman integral S equals to 0, which implies integral a to b S equals to lower Raman integral S. Hence S of x belongs to R alpha on closed interval AB. Now from 4 and 6, for all values of n is greater than equal to of m, minus epsilon upon 2 is less than integral a to b of S is less than integral a to b of Sn minus epsilon upon 2, which implies modulus of integral a to b S minus less than S integral a to b of Sn less than epsilon upon 2, so which implies limit n tend to infinity integral a to b of S minus integral a to b of Sn equals to 0, which employs integral a to b of S minus limit h tend to infinity integral a to b of Sn equals to 0, or limit n tend to infinity integral a to b Sn equals to integral a to b S, that is limit h tend to infinity sigma n r varying from 1 to n integral a to b of f of rx d alpha equals to integral a to b sigma n varying from 1 to infinity f n x d alpha. So integral a to b n varies from 1 to infinity f n x d alpha equals to sigma n varying from 1 to infinity integral a to b f n x d alpha.